Hey everyone, welcome to another deep dive with me and Erik. This week we're looking at the Pig Latin exercise. This is a fun exercise. It's a string processing exercise. The concept of the exercise is that you're talking to a friend and you want to talk in a code so that your parents can't hear you. And so we're following a few rules that enable you to change words from English into something called Pig Latin. There are 4 rules. I'm not going to read them out to you if you've not yet seen these. I'll put them on the screen here and you can pause and take a look at them. We have actually just rewritten these rules. After looking for all these solutions, we realized that people are getting a bit stuck and a bit confused in a few places. So we have simplified these, but that's not yet been merged. So you're looking at the version that everyone has been solving against right now. But if you actually go and solve it, once this video is out, there should be some slightly more streamlined instructions, hopefully. But yeah, we're going to look at a few solutions. We've got a whole range of things from one regular expression at the end that solves everything, starting off with lots of imperative code. We've got some pattern matching with Prolog in the middle. We've got all sorts of fun stuff coming up. So yeah, we're going to start off with that imperative solution. It's one of Bobahop's. It's in Go. And yeah, Erik, take it away. Tell us what's going on here. And I guess this is the first one, so you probably want to talk us a little bit through the algorithm as we go as well.
Yeah, so you start out with a phrase. So it could be multiple words. Mm-hmm. These words will just be the letters of the alphabet. So no numbers, no punctuation, none of that. Just letters of the alphabet plus separated by one single space. So the input format is quite straightforward. So what Bob's doing here is on line 13, he's creating a string builder, which is a specific type to efficiently append to things, of which you might not know how many appends there are beforehand. So we've covered that before, but that's the basic gist of it. So on line 15, you get strings.split, and then passing the phrase, and that separated character, so that's space. So you get back the words. So that's just a bit of setup. So within the loop, that's when the actual algorithm takes part. So so if it is if the length is not 0, then but that's pigified. So that's not the length of the word. That's the length of the thing that we are adding the Pig Latin to. So basically, what you should be reading that is if this is not the first word that we are processing. So that's because in the output, the words still have to be separated by a space. So that's what's being done there. But the actual fun stuff begins on line 20. So we have 2 Boolean conditions there. So the first one is if vowel square brackets word square bracket 0. So word square brackets 0 is the first character of the word. And then we index into the map vowels, which is defined on line 7. So that is a map of bytes. And in this case, those bytes are characters. And they're all mapping to a Boolean value. So that's just a little, I don't know if it's how many people use this like this, but it's just checking if the value is there. So in other languages, you might be using a set or something else, but this is basically the same thing. So we're checking if the very first character of the word is a vowel. So A, E, I, O, or U. And if so, then we have one of the rules that were specified in the instructions, which means that you basically you leave the word as is and you append A after it. And that's the only thing that you need to do. So that's the simple case. Then you have 2 special string beginnings. So if the string starts with XR or YT, those are also conditioned to be vowel sounds. So you apply the same rule. So that word square brackets colon 2 means give me a slice of the first 2 characters of the word. Then we're doing the same trick to see if it's in that map. So
just to interject there then. So the rule we've got here is if we've got a word that starts, I don't know, so we've got the word audio, which starts with AU. We leave the word as it is, but we add AY to the end, so that will become audio I would be the word. Yeah. But if we had a word that starts XR, so X-ray, we would have X-ray I, and that would be the word that we put out, I being AY and how it's pronounced. So that's sort of the first case and this sort of special case that get covered here.
Yeah, and so we append that to the string builder, and we do continue because we're done with this word. We're going to move on to the next word. The other case, the else bit, so if it's not like that simple vowel thingy, then we have more work to do. So we're actually going to start at position 1 because we know that the very first character isn't a vowel because we just checked that, so we already know it's a consonant. So what we're going to do is we're going to iterate in the string until we find a vowel. So that little for loop is basically iterating over all the indexes starting from 1. And getting on line 26, we get the letter at that position. So the very first iteration, there will be the second letter, etc., etc. Then we check if that letter is in the vowels Y map, which is a special case of the first one. So it has all those vowels in it, but it also has Y. And the reason why that is true is because the Y is a special case. So we'll get back to that in a bit, but one of the rules is if it has a bunch of constants plus a y, you need to do something differently. Okay, so what we're then going to do is to check for another special case. So if the current letter is a U, we check if the previous letter is a Q. And this is another special case if the word starts with QU or has a couple of consonants followed by QU, then you include QU as the thing that you move to the end before you append AY. Because for this, we previously just appended AY at the end, but now we're going to do something differently. Basically, what we're going to do is we're going to find up until a specified index consonant letters or things that mark as such, and we're going to move them to the end of the word first and then append Y. So for example, the special case queen, it starts with QU, and then you have een. It means that we move QU to the end, so we get een Q, and then we append AY, so we get een Q A. And this also works for consonants. So let me see. There are other examples there too. For do we have one? Maybe
so the word train, for example.
Which one?
Train.
Yeah, train is a good example. So we have TR, and we move that to the end, so you get eentru, and then you append AY, so you get eentray. And that's what's being done there. So we find the position where we need to move everything before it to the end, and that's what's being done on line 31 with the two slice with the pos colon and a colon pos. So it's actually quite a simple implementation. It works really well with just a couple of special cases. It uses those maps quite elegantly, I would argue.
Yeah, I like this as well as a sort of look behind. I'm sure we'll discuss look behinds at some point later on, but this concept of, I know a lot of other solutions check for QW as a string, and then that can be a bit heavy because you have to keep checking for it in different places. But the idea that you just continue until you get to this U and then check behind it for the Q is a nice way of approaching that, I think. I like that.
Yeah.
Cool. Okay, so that's the simple sort of imperative version. So hopefully if you've not solved the exercise, you're getting the idea of this algorithm now. We've got start with a vowel. We just return the word plus AY. Whereas if we've got any sort of group of consonants that might also include a QW, we move those consonants at the beginning to the end. We then put the rest of the word as it was at the beginning, and then we add AY. Cool. Okay. And we also have this one exception as well that you mentioned, where if we have a Y in the word, so if we have some consonants and then a Y, we treat the Y as if it's a vowel. So we leave that at the beginning, do we, Erik?
I think we do,
right?
yeah.
Yeah, we leave that at the beginning and then we move the consonants to the end. Okay, cool. So that was Go. That was Bobblehop solution in Go. Bobblehop has crossed the 100,000 rep on Exercism now, which is massive achievement. Puts him in the, I guess, third or fourth place all time. So yeah, awesome. So let's move on. Let's look at Kotlin. So this is a more concise solution, Erik. But I always, when I see these pairs of things, straight away, the thing that jumps out to me is that I know from solving the exercise that these are all pairs that are in the actual tests. So immediately I start to think, has this person solved the exercise, or are they just solving the test cases that are there? And I have to admit, the first time I solved the exercise, I took an approach like this, because the exercise talks about constant sounds and clusters. And so I very much interpreted these to be sort of consonant sounds. But you look very unimpressed when you see this. I know, Erik. Is that a fair comment?
Maybe slightly unfair to this person, because the instructions were actually really, really bad. I'm actually amazed that some people did implement it correctly. So no, I don't think this is. I should be unfair to this person, but it is hard coding.
Okay.
So the reason why it is very concise is also because it just adds all the exceptions, basically. Although admittedly, there are actually a couple of special cases that are in the instructions, so such as the XR, the YT, and there's a Y, although we don't really see that here, and there's the QU, of course. So there are special cases that you need to hard code, but there is no such things talking about THR or SCH. But let's just we'll forgive it. This is completely valid. This is our mistake. So let's just continue. So this person is defining the vowels, and previously it was a map. Now it's a list, but it's not just a list of those vowels itself, but also the two special cases, which sort of makes sense. There's a tiny downside to this, but we'll get to that. Then consonants is defined as all the letters in the alphabet minus the vowels. So that's fine. And then adding all the special cases. So you get the consonants has all the consonants, so the non-vowels. So the 21 letters that are not A, E, I, O, U, plus all those 2 and 3 letter exceptions, so the special cases. And then, line 8 to 10 is just to split the string into individual words, and then converting it to Pig latinified version, and then joining them together again with by spaces. So what they're using is actually quite nice. Kotlin. So on line 12, you see private fun string.toPig, and that means that you sort of you monkey patch or you extend or whatever your terminology is. I think it's an extension function in Kotlin, where you can add methods to existing classes that you don't own, because string is built into Kotlin, but you can still add a method. So that's why on line 10 you can call it.toPig, even though toPig isn't in the actual Kotlin standard library as far as I'm aware. So then within that function, you don't have to pass in any parameters. You can access the current value. You can access this method. So you are basically executing this in the context of the string on which it is called. So when is pattern matching in Kotlin? So take one is, you should read it as this.take1 or self.take1, depending on your language, or calling the take1 method on the current object. So that's just returning the substring, so basically the first character, but as a string, not as a character. And then checking if that is in that list of vowels. So that would only be true if it's A, E, I, O, U. And if that is true, we just return this plus A on the end. So that's just appending A. And the other case is when the first two characters are in vowels. So those are the last two special cases. So we got that covered. And this is completely valid. This is according to the spec. Then we get on line 14, we get a special case for QU. And this is where it starts to become a little bit different from the spec, because the instructions tell you that there is a constant cluster before QU, but actually the later tests have QU also at the beginning. But it might be that these instructions this was still valid. So it says that if there are consonants followed by QU, then you need to include QU. But this is very hard coded with just dropping one. So QU could even be at, a couple of other places later on. Although I tried to find words where there were two consonants and then QU, and I sort of failed. But it might be that there isn't actually really such a word in English, but maybe other people will find out. So, but the general gist of this is just that we're doing pattern matching, and we're trying to find out how many characters in the beginning do we need to, we first drop them. So that basically means we are omitting them, and then we're going to take them. So then we're going to add them. So drop and take are immutable, so they will return new strings. So you keep on working with the same string value. So drop three, take three means everything from the third character and everything up to the third character, after the third character and up to the third character.
I think what you were saying about words that start with QU, I think because they've baked the QU into the consonants as well, that case will just get sort of used when we get further on as well. But this is a good example of if there was a word that had two letters followed by QU, which I'm also trying to think of. I wonder, there must be some word that goes in front of queen, I would have thought, or quit, or like where you can concatenate a word before it.
Yeah, but it can't be like
rage quit.
A vowel.
Rage quit. There you go. That would be a good one. If you can not hyphenate rage quit. Yeah, that's true. Actually, there's obviously A and
that's
D.
the hard thing.
Yeah, I don't know.
Maybe there isn't. I don't know.
Okay, so just I was going to say, just to summarize. So we're presuming there's only ever one letter in front. We are checking to see whether we've got one letter plus two more. Is that? We know that it's not. We know that this isn't a vowel because, as you said, this pattern matches and does one at a time. And then we're just saying, forget the first three and get everything else. Then add the first three and then add the AY on top.
And then basically that's the same thing that we do, but just for the other three cases. So we're now looking into the consonants list. So we're seeing if the very first three characters are in that list. If so, we drop those three. We move them to the end. And we do the same for two, and we do the same for one. I'm not entirely sure what all of a sudden they're using subsequence instead of take, but I don't know.
I also feel that surely these... no, you do need this because you do have to compare it to this. Okay, yeah. So I was going to say, like, ignore me. I'm just I'm tying myself in loops. But yeah, so this works because we've got these in here. If we added another word that started with three letters like CHR, like Chrome, then that wouldn't match because it's not specified.
Exactly.
This series of things. And then we've got the final case, which is if none of these rules hold, which I guess is impossible because no word doesn't start with a vowel or a consonant, we would just return the string. But I guess that's just because this has to return something to compile, Erik, rather than...
It could throw an exception.
I like this, by the way. I like this as a syntax where it's sort of doing a map. And it's almost like doing a map reduce where it's reducing on the space in one function.
It's nice, really convenient.
Nice little Kotlin function. Yeah.
But
cool. Anything else to say on this one, or should we move on?
The general approach is to sort of find how many characters should be moved to the end of the string. That is something that we'll see later on. That's actually a very nice approach. So, and I like the use of the extension function. Yeah, agreed.
Yeah, I think this is really nice code. I mean, it's definitely like cheating in the spirit of the exercise. But as I say, this is exactly the same sort of approach I took when I did it. So I can't speak too much without being a hypocrite. But also, it's good code. There's definitely lots to learn and be inspired from in this code. So yeah, I'll give that a 9 out of 10. So next we come up to Scala. This looks immediately again a bit cheaty with the SCH and but a totally different method, Erik. It looks very elegant again, whatever's going on here. So talk us through it.
So this is it's the exact same solution as the previous one, but slightly implemented differently. Whereas in the previous one, you had the pattern matching, and that was responsible for also dropping things and then adding A. So there was a bit of duplication where you had to drop things and then you have to take things and then you add A. Whereas this solution tries to sort of dry that up. So the picket method function gets a string, and what it will do is it will return the number of characters that you have to move to the end. So if you go to, and it uses pattern matching for that. So the string is converted to a sequence, and then we use pattern matching on the sequence. And that's because you can't really do the pattern matching on the string. So on line 3, what you just highlighted, those vertical bars are ORs. So basically saying if the sequence starts with either an A, an E, an I, an O, or a U, followed by anything else, then you have to move 0 characters to the end. So that means we leave the string as is. So we don't do anything. So that's the case where we just append AY. Then you have, if it starts with QU, then we have to move those 2 QU characters to the end. So we're returning 2. Then there are variations. So line 5 is if it starts with the C followed by an H, or it starts with an R followed by an H, then we have to move those 2 characters to the end, etc., etc., etc. So that's all there is to it. And then the actual function where this is called is on line 16. It's a bit weird because it's defining like a lambda that's being called with the output. So this might not be as readable to people that are not used to this. But just read this as going over all the words, getting back the result of pigit, so the number of characters to drop. So that's that n. And so it will drop and take n plus ay and then convert it back. So the syntax it's quite concise. That might not be as readable to everybody, but that's what it's doing. Just
so
yeah.
So if you're struggling to read this, start here. So we split the string, we get each word out. For each word, we're finding this, and then we've got this closure anonymous function, whatever, that is getting called with this as the value. So the result of this pigit t is actually the n that's getting passed in over here. So it might have been nice to not make this anonymous, but it does make it nice and concise. And then this is just a join, I'm guessing, Erik, back. Okay, this one feels somewhat even more cheaty than the last one, but I like this approach of counting how many letters to move. I think you use the acronym DRY as well. For people that don't know, DRY stands for don't repeat yourself. So the aim here is, rather than having, as Erik said, lots of these drops and takes, or the drop and the sequence we saw previously, is let's just in one place work out how many letters need moving. And that feels quite an elegant approach. I actually like that a lot.
Me too.
Are you a fan of this approach, Erik, albeit the cheaty nature of it?
I quite like it. I'm a big fan of pattern matching, so I quite like how this can be read. I also like the thing that where you have the logic in one place. Although I'm not, I think maybe moving things into different lines would have helped a lot with the translate function. But sometimes this is what I do too, is just I want to get my solution very concise, and I don't bother with readability as much as I maybe should have. No, I like the solution.
Yeah, agreed. Okay, cool. So next we move on to Prolog. Erik and I always love a bit of Prolog. I don't think we're going to go into every minutiae of this, Erik, but you highlighted this for it's another nice example of seeing how the relationships of things in Prolog work really well.
Yeah, for line 1 up until 9, we can just ignore that. It's basically splitting the string and then translating. There's just a bit of strings converting to character list, etc. So we don't need to bother with that. Just the fun thing starts on line 11. So that's translate card. So you get C's, and C's is a list of characters. And what we will return is, unify, or whatever you want to call it, is piglet. And just return. So on line 12, it says starts with vowel. And this is the very first time that I actually see proper, well-named function here, I think. So starts with vowel is very typically how the instructions also describe it. So if it starts with a vowel, then you get a cut. So that's that thing with the exclamation mark. And basically says, we know the solution. This is fine. We don't need to consider any other solution. So we just stop here. Don't consider any other option. And if we found the vowel, it starts with the vowel, what we do is on line 14, we say append. And append is a predicate that takes 3 arguments. So it's a first list, it's a second list, and a third list. And the relationship between them is such that the third list is the second list appended to the first list. You can, in this case, we are passing in the very first 2 things as concrete values because we know them. So we get back the third thingy, but you can do different things with it. If you have a resulting list and you have the end, you can get the beginning, and we actually see that later on. So that's, if it starts with a vowel, append AY, and then we're done. So that's a simple case.
So just as a reminder to people that haven't watched previous videos and seen us talk about Prolog, the key thing with Prolog is the relationships between things. So in defining this function, I guess, I don't know if it's a function, but defining this, we're defining a relationship between CS, the characters, and Pig Latin. And this append is exactly the same. It's saying there is a relationship between these 3 things where if we have this thing and this thing is the concatenation of them. And so rather than having to return something, by specifying this relationship, Prolog knows what this is, and then that gets used further up in here, etc., etc. So yeah, those things get that's how Prolog works. It's all about relationships between things. Do we want to look at this start with vowel function quickly?
Yeah, sure.
Or do you want to carry on somewhere else?
I just want a small plug. If you want to know more about Prolog, we have an introduction to Prolog video that has a code example that tries to help you understand how this works. So you might find that useful. So it starts with vowel.
And it's a great language.
Prolog is a ton of fun. So starts with vowel is a predicate. So it's either true or false. And we are using, Prolog calls it unification, but it is basically pattern matching. So what we're saying here, if starts with vowel is called with a list where the first element is C, then it is true if the thing on the right side of that colon dash is also true. So vowel C is member C of the list. So that's a relationship between C and the list on the right, which is only true if C is a member of what's on the right. So just read that as if the very first thing in the list is a vowel. So that's just the Prolog way of defining that. And then you get.
And then we have these two special cases.
2 special cases. So you get where it starts with an X and an R, or it starts with a Y and a T. So what Prolog will do is when this is called, it will try to find any of these predicates starts with vowel for where it is true. And if so, it is true. And otherwise, it's false. So that's what Prolog will do. So, and Prolog is great at that.
And while we're here, we can see consonant is just the opposite. The inversion. Nice. Okay, so we were here, Erik. So I guess we're moving on to the next case.
So in this case, we know that it doesn't start with a vowel. So we can then start to find how many characters do we need to move to the end. So, and in the terminology of the instructions right now, it's called a consonant cluster, which might be confusing, but just read that as one or more consonants. So we pass in C and we want to get the cluster back. So we have to move to consonant cluster. And on line 20, the first case is if it starts with QU followed by anything, then the cluster is QU. So the cluster is the thing that we have to move to the end. So that's obviously QU because QU has to be moved and the rest has to be moved to the front. So, and then we do cut. So again, we have the exclamation mark because we're done. We don't need to consider anything else. If it isn't a QU, it starts, we check if it doesn't start with a vowel. So C's, which you think, hey, but that should always be true. But there is, this has to be done for Prolog to be able to infer the right things, basically. But let's just, it doesn't start with a vowel. I'm actually not entirely sure that this is needed, but maybe I'm just missing something because I don't see a call back to consonant cluster. But we could check. Just for now, we can assume that C So on line 24 is there's a unification. So you
Mhm.
can see that there's pattern matching or deconstruction, where we say the C's is unified with C and C. So basically saying the very first character is C and the rest is CS1. So then what's being done is we're doing recursion, but we're calling into a different function here. So we're calling into consonants prefix. So this is now properly acknowledging the fact that QU could have been, I don't know, the second or the third character, although we haven't yet found a word for that. So it tries to find if the rest, it tries to find the consonant prefix. So terminology is weird here. And that's also why we need to rephrase the instructions, because what's a consonant prefix if it isn't actually the very first thing? But it tries to find all the consecutive consonants, basically. So that's what's being done here. So there's a bit of trick here with relations. Map list is something that holds for everything. So we're saying everything in prefix is a consonant, and prefix is a prefix of C's. So that's basically saying the way you should read that is try to find all the things that's from the left to the right for which consonant is true. So basically take while something is consonant, but defined in a very Prolog-y way. So we just find all the consecutive consonants, and then we get our consonants cluster. So just if you want the details, you can dig it out yourself. But just assume that on line. Sorry?
I just agree.
Oh, okay. Okay, good. So if we just go back to where we started on line 16, we can just assume that we passed in C's, which were the characters of the entire word. We get back the cluster, so the things that start out, the consonants that start out. So we know what has to be moved to the end. So that's when we use append. But this time we are using it differently. And that's where that relation comes into place. So cluster is something that we have found. C's is something that we have too. So that's the resulting list. So we're basically saying, hey, we know what the full list is. We know how it starts. Can you give me the thing that you have to append to the beginning to get the full list? So it's almost like having a substring work in two different ways, where you can say it's really magic. So we have the full list, we have the start, and we can just say, hey, give me the rest with the same function that we used to append things. So same, well, it's not really a function, it's a predicate, but you get the gist of it. And then we have, well, the beginning, we have the rest, so we can swap them. That's what's being done there. And we can append AY, and then we get back our pig Latin. So that's actually all there is to it. It sounds very simple.
Nice. Yeah, it does. I think this bit's the only bit that gets a bit murky. The rest of it feels quite. If you know Prolog, the rest of it feels quite straightforward. But yeah, really nice. Cool. Thanks, Erik. So let's look at awk, and this is the straight away we can see we're moving into regular expressions. But this is what you would define as, I guess, a true solution. I mean, I think the Prolog one was as well, but this is a proper solution, and it's only 12 lines of code long.
No, I think this is probably the first one that really captures the rules very well. Although the Prolog one does sort of, but it has a bit more to it. So we can see all the rules here. So we see on line 7 that there is a match, so that's checking if a regular expression matches. And then the regular expression that we pass in is if it's, so the dash is the start. So if it starts with XR or YT followed by anything, then we return the original string plus A. So that's, you don't need concatenation, just with a space, then awk will handle that for you. So that's the rule, the special rule with XR and YT. Then what we do on line 8 is the rule with where it doesn't start with a vowel. So that's that square brackets and starting with the head. It's the same symbol, but it now has a different meaning. It's no longer the beginning of the string, but it's actually, it has to not match anything that comes after it. So not a vowel, Star means 0 or more of those. So read that as 0 or more consonants followed by QU. So, and that's the first pattern. So between the parentheses is a capture group, and we can refer to that on the right side. So basically the regular expression says all the consonants plus QU and then the rest, and then we flip those when we return them. So we start with M2, which is the rest, M1 is the consonants plus QU, and then plus A. So that is the QU rule. And this it matches QU at the beginning, it matches QU at the second position, etc., etc. Then you get a new rule. It says if it starts out with 1 or more, so it's this time consonants, so not vowels means consonants, and plus means 1 or more, then we capture that in a group, followed by Y with other characters. So that's where we have the Y be treated as a special case where we don't move the Y or whatever. We get the Y at the beginning, and all the consonants before it are moved to the end. So same logic with M2, M1, and A. And then finally, we get the normal consonants rule, where there has to be 1 or more consonants followed by the rest. So that will be either nothing or a vowel plus something else. And then we also swap that. So M2, M1, A again. And then finally, we get to the case which we don't even mention in code, where it starts with a vowel, but that's implicit. So then we just append A.
Nice.
So I really like this solution. This is really, really nice.
And just looking at lines 9 and 10, I guess part of me says, why can't we just move the Y into here? But I guess that's the example where you have Y followed by a consonant doesn't follow the same rule then, is it?
Well, Y has to be on the right side and in the right capture group, because it has to be at the beginning. It must not be moved to the end.
Okay, yeah. So it's staying.
Yeah.
So yeah, the Y stays where it is. Okay, got you.
Exactly.
Cool. So yeah, this is really nice. Yeah, amazingly concise, readable, follows the rules, everything you want in the solution, basically. So big credit to Glenn. Glenn always finds a good solution. So we're going to look at another of Glenn's in JavaScript. And this is basically the same, Erik, but slightly longer and a bit more playful. This, when I first looked at this, it took me a little while to. I sort of didn't read these lines and were somewhat confused as to what on earth was going on here. But these are just the Pig Latin versions of normal functions, Erik.
Yeah. So this is full Pig Latinified source code. So what Glenn has done is you see string.prototype and array.prototype. So everything that is a string inherits from the prototype. So it's like you can add things to the string, like we had with Kotlin, although this is a different implementation, where we're basically saying, hey, add something called itsPlay on line 4, and itsPlay is a function that takes in a single argument, and its actual implementation is calling this.split, but itsPlay is of course split latinified, so that's SPL moves to the end, and then appending a Y, and the same thing with match, map, and join, and then artisan pay ordway, so it's all Pig Latinified. The actual implementation is virtually the same as the previous one, but it's just having a bit of fun and using/abusing JavaScript's prototypical inheritance hierarchy. Nice.
And this, in case you haven't used your Pig Latin translator to work it out, says practice what we preach, which is a nice comment at the top of the whole thing. So yeah, this is, as you said, basically exactly the same.
Yeah,
it's just using slightly different.
You can just skip that.
Syntax, but
it's slightly different.
Exactly the same sort of regex. Yeah, this is slightly.
Yeah, it has the special case of the vowels in the beginning, not at the end, but well, I would say same difference.
And this is just our normal.
Yeah.
We won't go through that too much, but
just a bit of fun.
Yeah, credit to Glenn again. Yeah, we enjoyed that. What would have been, you'd have got bonus points, Glenn, if you'd also added some monkey patch into ESLint, so these could have been in Pig Latin T. Consider me slightly disappointed that you didn't do that. But yeah, I love it. Really good. You could have also, I guess, done higher order functions for things like, well, not higher order functions, but functions for things like return and if, and actually turn this into a whole Pig Latin like DSL. Yeah, I feel that's also an opportunity missed, Glenn. So maybe we get to see another iteration on here.
I think this was more than enough.
Some of that done. Okay. Erik thinks you've done enough. I always want more. Okay, so what's another one? I forgot to do this at the beginning. Let's just jump.
You should really build like a browser plugin thingy.
Yeah, or I should just actually do it. So let's jump into one of yours now, Erik. And this is the first one where we've got more complex regular expressions. And this is in C#. Again, very concise. Talk us through, I guess, the regular expressions, Erik. I mean, I think we can all see what they are.
Yeah. So,
but explain what this carnage means.
Well, it looks more. It looks harder than it is because I have used named capture groups. So that what you're now referring to, the question mark, angle brackets begin, and same with vowel and rest, are just helping us in the replacement, which we get to in a second, to refer to things that we've matched, but with names instead of indexes. So otherwise we would have \1, \2, \3, but now we can refer to beginning, vowel, and rest. So if you remove those, the regular expression becomes actually quite tiny. So begin is defined as head sign, which is the beginning of the string, or one or more spaces. And the reason for this is that in this regular expression, we don't split it. So we still have to match the pattern on words. So what we're doing is, well, the first word starts at the beginning, but the second word has spaces to the left of it. So that's what we're doing there. So, but we have to match it in pattern group because we still want to keep those spaces in the output. And what we then do is we match, well, we say vowel, should probably be vowels because you can also have the special cases. So it's either A, E, I, O, or U, or X, R, or Y, T. So that's another capture group. And then the rest is just, well, the rest. I use the word. I couldn't use dot because I wanted to stop with the spaces. So here we just assume that words are just letters. So this is fine. So the regular expression isn't that hard. So it's just beginning of the word, beginning of the string, or beginning of the word, with followed by a vowel. Oh yeah, you have a question.
I have a question. So in the exercise, if you've got the word, say, audio, where it starts with AU, do both of those vowels get moved, or
no, they don't?
Is it just the first vowel?
No, vowels don't get moved. It's just appending A.
Of course they don't. Okay, so if it starts with a vowel, that's enough.
Yeah.
Okay.
So it doesn't matter if there's like 3 vowels.
Okay. Cool.
So if that matches, then we do the replacement.
Yeah.
And the replacement is defined there. So we say beginning, vowels, rest, and then A appended to the end. So we're basically keeping everything intact. So we could have maybe done it differently because we don't need the capture groups per se, but it sort of gives it a bit of information about the actual structure. We do need them for consonants.
Bit of symmetry as well.
So for consonants, we do need them because we have to swap things around. So the beginning is the same with the start of the string or spaces. And then the consonant is, well, it's not a vowel and then question mark. So this is actually not entirely consistent because I'm actually saying it's either QU at the beginning or QU with a single vowel before it. So that should probably be star, but that would also work. So it should be star. Or it's a consonant, one or more consonants. But there is a little catch. So you have to specify that y there. So you get it has to be followed by, normally a non-constant consonant would be a vowel. So that's A, E, I, O, U. So, but we also have to be aware of the fact that the y must also be treated differently, because the y has to be kept. It must not be matched on that regular expression that you just had, that vowels plus thingy. So we need to make sure that it will match everything, but not the y too. So it must not be greedy. And that's what it's doing actually here. So
how are you? Yeah, where is it not greedy?
Because that's by default. By default, it's not greedy.
Oh, is it lazy by default?
The way that it's defined here, it is.
Well, if it was lazy by default, okay. I'd have thought if it was lazy by default, it would only capture one of these letters if it could.
Yeah, but it has,
rather than capturing as many of them as it could.
It's a good question, but it does work. So
the reason I'm asking this is I was playing with this exercise last night, and I tried this approach, and I found it didn't work because of greediness, because it would capture the y in here and then ignore the fact there was a y here. So yeah, I don't know. I'm intrigued. I'm gonna.
Yeah.
We'll.
Regular expressions.
That can be a lesson, a test for you afterwards to go and see if there's how this works, or if there's a test case that makes this work or something. I don't know.
Maybe.
What is if we see, you can, little tip for anyone Exercism doesn't know, you can always click on past and see the tests here. We can look and just see
line 21, test 21.
So I wonder if you had a y as a third letter here, whether this would still work or if it would fail. I suspect if there was another letter here in between the M and the Y, this would fail.
We could check.
That's my suspicion, but we can do that after.
You can always do a negative look behind. So a look forward.
Yeah, because that's what I started doing last night, and then realised I had better things to do with my life than trying to do a negative look behind in preparation for this video at midnight last night. But yeah, okay. That was why right at the beginning of the video I mentioned look behinds, because I thought we would have to end up using one when we got to regexes. But okay, so there's a small chance Erik cheated and coded this to the tests, which I'm going to enjoy taking some pleasure in. But we do have another regex solution here, which is a regex solution, but by the look of it, a very cheaty regex solution, Erik.
You can see that's cheating
based on a couple of things that immediately.
How many constants do you see? Those are not 21 consonants.
Yeah,
definitely not.
Yeah, this is definitely cheated.
So this is cheating, but that's the negative thingy. So
yeah.
Well, this is just a bunch of special cases basically. It's all doing the same thing, but it's hardly. It's not very readable. So backslash B is a word boundary. The beginning, the question mark I is case insensitive matching, which I don't think you actually need because everything is in lowercase, I think, but maybe not on Python. So I just wanted to show you that it is possible to create a solution for this that works. But, I'm not sure if it's as easy if it would be doing everything properly.
Yeah. So this is someone doing an X-ray. What is
it a negative look forward?
Mark exclamation.
Let me see.
What
was it like?
Maybe it's an optional.
It's a negative look ahead.
Positive look forward.
It must not be followed by.
That's negative.
That's a negative look ahead. So an X not followed by an R.
Want X and R? Does that mean that we handle the XR case? Oh, I don't know.
Yeah, but this is
going to be too complicated for us to work out.
Too weird. And in the end, you see that.
I guess because we don't want, if it starts with an XR, that counts as a vowel, so we don't want to move it.
Yeah, something like that.
That makes sense. So it's negative look ahead. Okay. Fun. All right, I'm not gonna suggest we go through this, but I think if you scan through it, it's quite readable. It's the C and the Q where you haven't got an H that follows it, and you've got a Y, but you can have an H that follows it, but you don't have to. Here, you have to have a Y that doesn't have a T or an X that doesn't have an R, followed by some consonants afterwards.
At least two.
That are not followed by a Y. At least, that's confused me. At least two. That again must just be an artifact of the tests. And then,
but that's what
that's not followed by a Y.
The negative look ahead was what you would expect with mine solution, probably. Like consonants, but not followed by a Y.
Well, no. I don't know if I would. Because I would, on your solution, and we could end up getting a bit deep here, because you do what? Because you're trying to include the Y here.
Yeah, but I meant on the left side.
So you need almost like another group. I don't know. I don't think it's that. I don't think a negative look ahead would work.
No, it must be something,
because you do want to capture it.
It can't be. It must be.
Yeah. I think you need a. No, I don't know. This is let's leave this. I mean, I think we could spend the next half an hour wrestling about this and trying to get there, but I think it's probably better to leave this as a task for the reader. So Erik and I clearly don't know enough about negative look aheads and look behinds to have intuition about this. So tell us in the comments. Good job. Yeah, or greediness or laziness. I'm pretty sure it's greedy by default, not lazy by default. But maybe I'm wrong. But yeah, tell us in the comments. This is a good thing where we can learn from all of you. Link to your solution. If you have done a solution for this where you've cheated and hard coded the tests like I did, go back and do another one now, having seen all of these that does it properly, and then post a link to your solution below. I hope that was fun. I hope that was interesting. Thank you for watching. Thanks, Erik, for talking us through all of those. Have a great week, and we'll see you in the next video. Bye for now.